Okay, I'm going to look at a proof by induction. I'm going to try and prove this result, which, just looking at it, is a product. This bracket times this bracket times this bracket times all the way up to 1 minus 1 up n squared is equal to this. And interesting to note that this result stands for n greater or equal to 2, because the first term involves n is 2. So, as always, start with the basis step. And here, I need to consider n is 2, the first case. So this is unusual. Most of the time it's n is 1. But here, the basis step says n is 2. Let's check this out. I want to check the left-hand side is going to be 1 minus 1 upon 2 squared. 1 minus a quarter is 3/4. Check the corresponding result for the right-hand side, making sure I'm clearly showing what I'm substituting in. 1 plus 1 over 2 lots of 2. Sorry, there's an early error avoided. N is 2 in this case. So this gives me 3/4. Therefore, result true for n equal to 2. And the basis step is done. On to the inductive step. Create a little bit of space. Inductive step. Now, as always, I'm going to start by an assumption. Assume the result is true when n is equal to k. And I'm going to write down what that means, i.e. I'm going to assume that 1 minus 1 over 2 squared times 1 minus 1 over 3 squared times all the way up to 1 minus 1 on k squared is equal to k plus 1 on 2k. I'm going to assume that is true. What I then need to try and do is show the result follows for n is k plus 1. So now try to show the result follows for n is k plus 1. And again, I'm just going to write down what that actually means, i.e. I'm going to try and show that 1 minus 1 on 2 squared, 1 minus 1 on 3 squared, times all the way up to 1 minus 1 on k plus 1 squared is equal to k plus 1 over 2 lots of k plus 1. That's my job. That's what I want to try and do in this inductive step. So now let's try and do it. So left-hand side of this equation here is 1 minus 1 on 2 squared, 1 minus 1 on 3 squared, all the way up. I'm actually going to write the last two terms. 1 minus 1 on k squared was one before it, and then the last one, 1 minus 1 on k plus 1 squared. Now the reason I've done that is that I can see in here, this is an expression that I'm assuming is equal to this. So this is where I'm going to use the assumption. So I'm going to replace this expression with this result here. So this becomes k plus 1 on 2k multiplied by 1 minus 1 on k plus 1 squared. And I'm going to write using the assumption, so I know exactly where I've used that in my argument. And now I've got to do the algebra. What can I do with this? I want to cross multiply over here. So I've got k plus 1 on 2k times, that's going to be k plus 1 squared minus 1 all on k plus 1 squared. What happens if I multiply this out? Let's tidy this up. K plus 1 all squared is going to be Well, let's do this, k plus 1 on 2k times, that's going to be k squared plus 2k plus 1 minus 1 will disappear. So that's k plus 1 squared. And I'm getting close now. What can I do with this? Well, the k plus 1 will cancel. A k will factor out of this and will cancel here. So that will leave me with k plus 2 on 2 lots of k plus 1, which is equal to the right hand side as required. So I've completed the inductive step. But as we've talked about, both of these steps together are meaningless. I haven't finished my proof until I've claimed the principle of mathematical induction. So at the end, I still have to finish off by saying, hence, by mathematical induction, the result is true for n is equal to 2, 3, 4, n belonging to z plus n greater or equal to 2. A similar question for you to try. Can you prove this result? A similar product, 1 minus a half times 1 minus a third up to 1 minus 1 upon n equals this. Again for n greater or equal to 2. I'll leave you to prove that by induction.